So if we have to draw the particle diagram, I'm gonna draw this as if it were a salt. And how are salts drawn? You have this the negative anion that is bigger. You don't have to draw in all of them. And then you're gonna have the positive cation.
Is that HCO3?
NaHCO3. So the HCO3 is the negative side, right? And the Na is the positive, the Na plus is the positive side. So this is literally how we draw all salts. It's not how it is in real life, but it helps you think that it is a salt, that is an ionic bond, that it is brittle, that it has a high melting and boiling point. It helps you think of some things. In real life, is it organized like that? No, but it is gonna help us. Now the intra bonds are ionic or covalent, right? And they are bonds like the magnets. This is positives and negatives, but they behave just like that. They attract each other, so they are not sharing anything. They are just being attracted, the positives and the negatives. And that intra bond, the intra bond is going to be ionic. All those are gonna be joined by ionic bonds.
Intrabonds attract
Intra bonds are ionic or covalent, is what makes a molecule or a compound. Inter is like the interstate, it's in between two states, right? So interbonds will be other types of bonds, which we do have. Well, no, in here we have another intrabond. Where can we see the other intrabond? This one is ionic. Now in here, what type of bond do I have between the H, the C, and the O? No, that's within. That's what's making that polyatomic ion. The polyatomic ion is being made. The salt is being made by an ionic bond, but the polyatomic ions are being made by what type of bond? Covalent. It's a covalent. So those are intrabonds. Salts don't have interbonds. I mean, they say they have London dispersion forces, which everything does, but intra. They're all intra. So whatever makes the polyatomic ion, it puts it together, right? It's covalent. The polyatomic ions are one thing. And they're treated as one thing. They're not treated as hydrogens, carbons, and salute. No, they're one thing, right? Yes.
The bond between the Na and the HCO3 is
Intra, because that's an ionic bond. That's what makes the salt, right?
and the other one's inter.
No, this one is in. They're both intra.
They're all intra. All of them are intra?
In this, yes. One is covalent, which is making this thing, and one is ionic, which is making the salt.
And would an interbond be like one
So we're gonna do interbonds in the next one. Let's go ahead and look at, there are no inters, they're supposed to be London dispersion forces, but I'm not gonna confuse you with that.
HCO3 is connected by interbond.
Yes, it is making one polyatomic ion that is sharing the electrons, right? When you share electrons, that means the electrons are all shared. So that's an intrabond. You are sharing between, you are intra. You are being attached like that, you are intra. Now let's look at muriatic acid or hydrochloric acid. You will have the H plus or the H3O plus, little, and then you have your Cl minus, bigger, but it's in water. This one is in water. That will be also a polar covalent bond, but right now we put it in water, and because it is a strong acid, it dissociates 100%. So do not put them together. And I know we haven't reviewed this in a while, but it's important to not forget it. You put at least 3 molecules of water. Now we are going to have interbonds. Oh shoot. Yeah, so the interbond is going to be my interbond is going to be this pink, and that's going to be between what and what? Yes. This bond between two different species, like two different states, they're not really sharing, they are not really attracted like an ionic bond where you stall the electron. They're not sharing or stealing. Sharing is covalent, stealing is ionic. That's not happening here. This is simple. I'm really close to another one, right? And we feel an attraction. We're not sharing, we're not stealing, right? I didn't grab the electron. I am not sharing my electron. We are just, the water is close to something negative and there is an attraction in there.
So, interbonds, there's an attraction.
Yes, there is an attraction, but this attraction is weaker, right? And it's just because it's two different species all together. That's just water, and that's that. And that is called, what is the name of that bond? Ion dipole. So it's a hydrated shell that is formed. They form a hydrated shell, and it's all around it, and they're all just attracted, but they are not bonded to it. Just like that, they're literally just a slight attraction. They're movable in there too, yes.
So like just with the water, like two O's and H, would that be an intrabond?
That is an intrabond. So in here, we have these bonds that are making water.
That's intra?
That is an intra. What type of bond is it? Polar covalent.
But it's in between two different things.
No. It's putting water together. Water is one molecule. Water is the Mickey Mouse thing, right? It's one thing. Right?
Is it?
You want me to bring you a water?
So inter is between like two different molecules, but intro makes the molecule.
Yeah.
Cl and Cl and oxygen, water on.
Look, one water right there. That's one thing.
I want
Wait, does ion dipole, does that only occur when
When you put a salt or an acid, a strong base in water, you have those ions in solution. They are very strong. This is so strong that this is the reason that the chlorine will not attach back to the hydrogen. That's the reason it's so strong. This is so stable. So stable, that hydrated shell is so stable that it will not want to go back into reacting with anything. So the ion dipole, water is a molecule. How will it attach to another molecule? There will be hydrogen bonding right there. But it's going to be loose enough that it can go attach, and you know? It's not like salt that is attached, period. They're so strong, right? This is not. This is a weak force. It's a hydrogen bonding. But this one is an intrabond. That's what makes up water. And then how water is surrounding and what is attracting is an ion dipole bond. Now, what did you make? You make carbon dioxide. You make carbon dioxide. You can draw it. You will have a water line because when we put that, this is still going to be in solution. And you're going to have the carbon dioxide that is going to be either one carbon and two oxygens if you want to draw it like that. Or you can simply put, because we haven't learned that, you can put that as a gas. So however you want to do it, it's fine. That's a carbon and two oxygens on the side. That's how it really bonds. That's how it really bonds, but you don't have to know that because we haven't studied that. So if you just put CO2 and as a gas and coming out, that's fine. The same thing that we did the HCO3, that's not what it really bonds like, but we're just gonna put it because that's just what we know right now. So the carbon dioxide escapes We also made sodium chloride. So the chloride spectator ions will be there. The sodium is also part of NaA. It's not gonna bond with anything. They're both gonna be surrounded by water.
Does it matter which one's big or small? Or is it-
Yes, the Cl should be bigger because he gained that electron which repelled the other electrons in the shell, and it should be bigger. Should definitely not be smaller. And it should never be together with the other one because this is NaA, it's completely ionized. And then we have carbon dioxide, oh, we have water. The other thing that we had was water, so you can even draw more waters if you want. Now let's look at the bonds. Which ones are the intra-bonds in this sketch?
The waters.
Waters have intra-bonds that are polar covalent. And they're not separated, that's wrong. Obviously they're attached or they wouldn't be intra. So those are attached. They're sharing electrons. The oxygen keeps them longer than the hydrogen, but they're sharing. Although the oxygen is more electronegative, so if you had to draw the direction, what's the most negative, you will always be pointing to the oxygen.
Wait, for Na plus, why are the positive hydrogens binding with positive?
Yeah. Should it not be the opposite way?
Na plus, that's the oxygen.
Oh, right.
The oxygen is the most negative one. Now, what bond? So we have some interbonds in here. What do we have in here? Between what?
The O and the N.
So those bonds are called what? Inter, but what is the name of that? Ion dipole. For this one and also for that one. These are ion dipoles and these are ion dipoles. Now, what is the bond that happens between the two water molecules? Not polar covalent, in between the two water molecules.
Hydrogen bonds.
Hydrogen bonding because you have an H in between two O's. It could be N, O, or F. So that's hydrogen bond.
What is that? Is that inter or intra?
Hydrogen bond, you have a water molecule, and then you have another water molecule. It's a bond in between two different species. Inter, like the interstate. It's got one state and another state, right? And the bond in between two different species is like the interstate because it's in between two states, right? This is a complete thing. This is a complete thing joined by covalent bonds, right? But when those two are gonna be attracted to each other, that's gonna be inter-hydrogen bond, right? Right? Okay, sure, that didn't sound very right. So what is the bond? What about here? What bond do we have in the carbon dioxide? And what is the name of that bond? It's non-polar covalent, although you don't know that. You can just write covalent because that's based on geometry. The fact that it has two different things will tell you it's polar, but it's not. Because the dipoles go to each side, so they cancel each other out, but you don't know that. So just calling it covalent will be good enough. But that is an intra-covalent. Ionic, covalent, metallic are intra. All the other ones are inter. So I think we addressed everything. Hydrogen bond, dipole, ion dipole.
The CO2 is intra.
what makes it, what puts it together. If you wanted to, if this is confusing, you don't do it. But if you were to have CO2 molecules next to each other, there'll be something they're called London dispersion forces. But we haven't learned that yet, so don't put it.
What are they called?
London dispersion forces. It's when automatically, it's what you used to call in biology van der Waals, but van der Waals is the bigger intermolecular forces, right? But London dispersion forces is when randomly all the electrons go to one side and then you have an instant dipoles that are happening all over the place. Which is the reason that some things, I don't know if it's geckos or whatever, they can climb on windows. It's because of those London dispersion forces, and we haven't studied them yet. So if you want to ignore that for now. Any questions on this? Okay. Now, what else do we have? So, sodium bicarbonate is called what in real life? Baking soda. So that is baking soda. This is hydrochloric acid, right? And it is called in real life muriatic. It's on the other page, you may have seen that. So if you go to Home Depot, you don't ask the people, oh, give me some hydrochloric acid. They say they don't sell it. But if you ask them for some muriatic acid, they'll bring you a bottle of hydrochloric acid, 12 molar, very strong. I'll have to have protection if I use it here. So some of the things you can buy out there are just as dangerous as some of the things that we treat with a lot of respect over here. If you ever buy something like that, read the SDS just to see how to protect yourself. If you happen to inhale it, you happen to drink it, you happen to spill it on you, it'll tell you how to take care of yourself. If you have it too much, you can always call the paramedics, but you need to give them the SDS so they already know how to start treating you if they need to. So baking soda one, we couldn't even need that. But how do you find the molar mass? Sodium is 23, that's the grams per mole of sodium. Hydrogen is 1 gram per mole. Carbon is 12 grams per mole from the periodic table, and oxygen is about 16 times 3. You add them all up, that better give you 84.
How do you get that?
Because you look at the molar masses of each one of those elements in the periodic table. Yeah, we had that earlier on, not for this test, but for the last one. We found molar masses.
So that's not going to be in
Not likely. But you still need to know it because things are kind of cumulative. So you may have something like this, like it showed up in this lab, and the next topic is stoichiometry, is full of math. We are gonna go full blown on math. HCl, this is 1, this is 35, and da-da-da-da-da. Bond, I'm talking about intrabonds, as described.
Not covalent or ionic.
That's exactly what I'm calling, intra. It's all covalent or ionic. So this is what joins us out? An ionic bond. Let's don't talk about this other bond. We know that's covalent, but let's just say the salts are joined by ionic bonds. If this were not in solution, but it was just a hydrochloric acid or hydrogen chloride, what is it joined by? Polar covalent, right? You can't just write covalent. Whenever we study bonds, it's going to become more important to write the polar covalent.
Do we not have to do the long runs of HCl?
Yeah, all of them.
36.
The state, what is baking soda? A solid. What's hydrochloric acid? Aqueous? No. It's aqueous because you have ions in solution, although we're assuming it's all liquid, but no.
What if we say gas?
It's not a gas. Hydrochloric acid in this case is not a gas. You're going to have the actual hydrochloric acid, and we're going to have baking soda, and we're going to mix them together. And we're going to look at the pH and how the indicators change in color. That's what we're going to be doing. You can finish that chart. Then you have this. Make sure you do this before you leave. What we have is one of your fellow classmates made this indicator, and anthocyanin is what is in there that helps it turn different colors. This indicator, depending, is a natural indicator that will tell you something is and how acidic it is. I mean, how crazy is that? You can actually do this at home to find out fairly well what the pH of something is, all the way from, you know if you are about this, am I about here? What is the pH? Right, so you have a pretty good idea of how acidic or basic any solution in your home is by using red cabbage. You boil it, get the water out, and it's pretty good. So I put quite a few solutions, so I want you to use that to tell me about what pH and what is the solution that we made and what pH was it. So we have them in the back. You just have to go in the back and say, hey, the baking soda was this pH, the vinegar was this pH, the water was this pH, just to look at different pHs, which you can do at home with anything you have at home. You can take some of it if you want, because I have more than enough. We've already used it, and we only used a little bit. Actually, we're gonna use for the other lab. And the rest of the class is between doing this and doing your master in chemistry and asking questions.
Use the colors up there, like, this is all black and white.
What?